Okay, but let's keep on with this story. At a single wavelength, and that's going to be key in a moment, for one given wavelength, the angular diameter of this is 2.44 lambda over d, right? We've all learned that. So lambda is the wavelength, d is the diameter of whatever the diffracting object is. And so there's this inverse dependence on d. Large particles make small diffraction patterns. Small particles make, did I say that right? Large particles make small diffraction patterns. Small particles make large diffraction patterns. So if you want to see really beautiful, easily visible diffraction rings, you need small diameter particles. Okay, so that's why we said this has to be a small diameter water droplet. Now what if we replace that water droplet with a random array of water droplets, all of the same size? What changes over here? That's a question. What's that? Actually, nothing changes over here. If it's a regular array of, if you take these and put them at regular distances, then you can get fringes in this pattern, right? It's a extra interference pattern. But for a truly random distribution, actually nothing would change. We would get exactly the same pattern. And so if we have randomly distributed water droplets, even though we're not looking at just one water droplet, we expect to see this from the cloud. Now, if we take away those randomly oriented one-sized water droplets and replace them with a randomly distributed collection of random sizes, now what changes? Well, each one of these drops creates a diffraction pattern with a different width, and so they all wash out. So if you have a wide range of sizes, you don't get any visible diffraction because they're all creating a diffraction pattern, but the red band overlaps the blue band of another droplet, which overlaps the green band of another droplet, and it just gets to be a white smear. Here's a picture of a corona, which is what we're describing. This is diffraction from spherical water droplets, theoretically. And you see that, well, the first thing that should bother you is you see red and then blue. And you say, now wait a minute, I know that the diffraction angle is proportional to the wavelength, and that's backwards. No, it's not backwards, I've just cheated. The inside is overexposed. And so the first order blue ring is overexposed. This exposure only captures the red of the first order, and this is the blue of the second order. Now I want to give credit to my co-author and my good friend and colleague, Paul Neiman. This is his picture. All the other pictures that I'll show you are mine, but I just love this picture so much that I like to use it. He gave me permission to use it. So Paul Neiman is a meteorologist at NOAA in Boulder, and he's a great photographer. He takes a lot of nice pictures. So there's a circular pattern, but here's what happens when we get what's called an aureole, which is a corona that's not very nice, kind of a crummy corona. So here's the sun or the moon. In this case, it's actually the moon. And you see a ring of light, but you don't see much color. If you're up close and you look carefully, there's a little bit of blue light, but basically you don't see much coloration. And so you see this a lot of nights when there's a full moon up and there's a thin cloud blowing across the moon. You'll see this. What it is diffraction, but the drop size distribution is fairly broad. So you get a bunch of diffraction patterns that overlap. And so you get color, or you get light, but you don't get much color. So that's not as much fun. Iridescence, though, is what we were looking at before. This comes about from spatially random clumps of droplets. Each clump is locally uniform, and each clump has a relatively narrow drop size distribution. And so there's a random distribution in the cloud of drop sizes, but at each point in the cloud, you can sample over a small area and find essentially the same size droplets. When that condition, or those conditions are met, you can get this kind of effect. But let's go back to my mystery. What was bothering me is what bothered me again a number of years later. These are pictures, again, from my friend Paul Neiman, and I can't remember, one of these might be mine too, but these pictures, we had collected a bunch of pictures that we had that were showing coronas and iridescence in what are called wave clouds. This is when air is flowing and it runs into a mountain and bounces up and then forms a cloud and then bounces back down. So you get these on the lee side of mountains quite often. And we were living in Boulder, Colorado at the time, where you get these all the time. This kind of thing happens frequently. And so we had taken a lot of pictures of coronas and iridescence in wave clouds, and we started doing some meteorological analysis just because we were curious. And what we found is that over half of our pictures that we had were taken during conditions. We had to go back to the weather maps and look at the meteorology because we didn't do the sampling real time. The meteorological maps told us that these clouds had to be ice. But how could they be ice? Because ice crystals are too large to create these patterns. So we really were stumped. And so we went to a guy named Andy Heimsfeld at the National Center for Atmospheric Research in Boulder. And we asked him, how can this be? This is one of the most world-famous experts in the particles of clouds. And so we asked Andy, what's going on? Because this is what you see. These are pictures of ice crystals that he sampled on an airplane flying through the bottom of a wave cloud. But he just smiled, and he stood up, and he walked away. I was like, whoa. Luckily, he came back. And when he came back, he was carrying a photograph. And he just plopped it down and said, there's your answer. Guess what the picture was? It was this. Here's ice crystals that he sampled at the top of a wave cloud. They're not these big, these pictures are on the same scale where 100 microns is about that big. These are like little 10 micron quasi-spheroidal ice droplets. Guess what? You can get diffraction patterns just fine from these little particles. So these little particles explain all of these cases. And we said, oh, I get it. So we published a paper. We offered co-authorship to Andy, but he said, oh no, that's fine. And so we wrote this paper, published it in 2003, I think, and then we just sort of went on, did the rest of the things that we're actually paid to do. But last year, in February, one of the things I do with my research program is I build and use LiDARs, or laser radars, and this is a picture of one of my graduate students with a LiDAR system that he built. The laser beam is shooting through a hatch that opens up in the roof of our building, and the laser beam goes up. We send a pulse of laser light, and as the pulse travels vertically, it's scattering light in all directions, and some of that light is coming in the back scatter direction back to our telescope, which is right here. And we're collecting that and counting photons with that. Actually, this one isn't a photon counting, but we're measuring the brightness of that backscattered light as a function of time. And as a function of time can be turned into as a function of range. And so we can measure the scattering distribution as a function of range. And this particular LiDAR has a dual polarization capability, which allows us to distinguish between liquid and ice. And guess what? I was going home. Actually, my wife had picked me up, and it was kind of late. It had been a long week, and I was going home, and I was really tired. So I sat in the passenger seat of the car, and I laid the seat back so that I was kind of looking out the side window, and I saw the moon with a beautiful set of corona rings around it. And I did some quick math and figured out in my head that that cloud is way too hot, way too cold to be liquid. So I knew that I had another golden opportunity, and so I said, sorry. Go ahead and pull in the driveway and go in and eat dinner, and I'm going to go back to the lab. So I ran back to the lab, and I turned on the LiDAR. Note that I didn't pick up my cell phone and call the graduate student and say, go to the lab. I actually did it myself because I was curious enough that I just wanted to do it. So I turned on the LiDAR, and we were really lucky that night that the cloud was right in the right position, so I was able to sample at least the edge of the cloud. And I got this really cool picture of the moon with a corona around it and my LiDAR beam hitting the cloud. This is a wave cloud, very thin wave cloud. It meets all the requirements we just talked about, and the polarization signature told me that this is absolutely, without any question, ice. And so we had, for the first time, an actual measurement that showed ice in wave clouds that are causing circular coronas, which means that it has to be the explanation that we published as a likely explanation earlier. So this will be published soon, and it was exciting. Okay, let's talk about rainbows, because all of you are going to be asked someday about a rainbow. So what causes a rainbow? This is a double rainbow over my house, actually, last month. No, today's October 1, so 2 months ago. This is August. And you can see that there's a primary rainbow, and then the secondary rainbow, two things should jump out at you about rainbows. And the first thing is that the primary rainbow goes from blue to red, inside to out. And the secondary rainbow, if you look closely, goes from red to blue, inside to out. So the color order is reversed, right? Somebody's going to ask you about that someday, so let's make sure you got that all ready to answer. The other thing you can tell from the geometry of this is this picture isn't so obvious, but you can see that there's a tree over here, there's a vanishing point for the shadow, my shadow here. So they're all kind of going to that point. What these shadows are all doing is going to a point right here, which is called the anti-solar point. This is the point away from the sun. In other words, if you stand there and let the sun be at your back, look for the shadow of your head, that's the anti-solar point. And the rainbow is always a circle around the anti-solar point. So where do you look for a rainbow? You look away from the sun, and you look in this large, it's a very large phenomenon, isn't it? A rainbow is a very large circle, 40 to 50 degrees in radius. So here's the basics, just using geometric ray tracing of rainbows. Ignore the top one and just look at the bottom one for now. If we bring white light in, that black ray represents white light, that's all right. And when it hits the raindrop, what happens? First thing that happens is some of the light reflects. I don't show that. But second thing that happens is the rays will refract or bend in the water, right? And you can calculate that with just Fresnel coefficients. But you also know that that's wavelength dependent. And that's because the refractive index that you have to plug into the Fresnel equation is a function of wavelength. This is called dispersion. Same thing that we use in lens design, dispersion of glass, and this is dispersion of water. So we have blue being bent more than red. At the back of the raindrop, most of the light, I don't show it, but most of the light goes right on through. Okay, that's a common misconception. A lot of people, even textbooks I've seen, say that this is a total internal reflection. It is not. If it was, rainbows would blind you. Right? So it can't be right. What are they thinking? Well, they're not thinking. So most of the light goes through the raindrop. Some of the light reflects off of the back of the raindrop. It is not a total internal reflection, but it is very near the Brewster angle. Okay? So what does that mean? It's going to be highly polarized light that reflects off the back of the raindrop. That light refracts again at the interface. And so if you go through the polarization analysis, which is, I want to talk about that because Paula and a number of people here are studying polarization. You can, in fact, I remember when I took a class here as a graduate student, Dr. Marate, who I guess isn't teaching anymore, but I saw him yesterday and visited with him. He taught us a class on electromagnetic effects, and one of the problems that he had us solve was this problem. He had us calculate the degree of polarization of rainbow light from the Fresnel coefficients at these various interfaces. And it turns out that you find that it's, I forget the exact number, but theoretically it's around 90-some% polarized. And the orientation, these are competing orientations, right? You get one polarization here and one polarization here and the same polarization here. But the net effect is that this dominates because it's near the Brewster angle, and so you get polarized light. And is this upside down? You look at that and you say, well, wait a minute, that looks upside down. Because remember I said blue is on the bottom, red is on top? You have to remember, this is just like doing imaging with a thin lens or whatever when you're in Optics 101. It's not where the rays are, it's where they appear to be coming from. And so the red light appears to be coming from a higher point than the blue light. And so the blue light is appearing to come from the bottom. And so when you look at it, you see the blue light and then the red light on top. So that's, in geometric optics speak, that's what's happening to the rainbow. With a double rainbow, the secondary rainbow, it's the same thing except for the light's coming in at a different angle. We still have a refraction, but we have two reflections at the back. And then we have another refraction here. And the color order is reversed. And so you can see, because of that extra reflection, we get the reversed color. So the answer to the question that your grandmother or child will ask, why are the colors reversed in a secondary rainbow, is because of the extra reflection at the back of the raindrop. It's a mirror. And if you wish, if you're really a mean-hearted person, you can get rid of a rainbow. Because What's the axis of